Hello, hello, testing, testing, one, two, three, four. Type this number in. I'll be starting in just a second. Just trying to send this link. www dot dot be dot be slash p k k underscore 35E 35E P 2A. PKK 35 EPR 2A. See if this works. What? Start this over again. U dot BE backslash PKK
Yeah, thank you for sharing.
You're welcome.
You're making me a new video.
No, I got it working actually.
Okay. Right. Yeah,
Okay, okay, let's see. Testing, 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 one, two, three, four. Testing, testing, testing. Okay, here we go. Start. Okay. This is part 2 of chapter 9, mechanical ventilator graphics. I will be beginning 155, first section. We'll make it small, any major sections. Okay. Okay. Page 5. Okay. Chapter 9, page 155. Let's see. We'll start with the first complete section. That's changes in the pressure time curve. The curves in figure 9-9A represents the normal pressure and flow scalars obtained during volume-controlled ventilation. Note the slight pressure deflection that occurs just before the start of the breath in figure 9-9. A represents the patient's effort to begin inspiration. This is therefore a patient-triggered breath. A and B of figure 9-9. One ventilator parameters have not been set correctly. First, the ventilator is not sensitive enough to the patient effort in part B. Note how many centimeters of water pressure are required to trigger the breath. Range would be a pressure drop of about 1 to 2 centimeters of H2O or water below baseline in adult patients. Second, look at the way the pressure curve increases to PIP in part A compared with part B. Compare the two set flows in part A and B. These are examples of breath delivery by a ventilator that holds flow constant at the set value regardless of the amount of flow the patient tries to receive. Open parentheses. The Puritan Bennett 840 during volume-controlled continuous mandatory ventilation, VC-CMV, is one example of this type of ventilator, close parentheses. The flow the operator sets during volume-controlled ventilation is the maximum flow the patient can receive. Their setting changes could the respiratory therapist make to accommodate the patient? And the answer to that is asterisk at the bottom of the page. Increasing the set flow may be required to meet the flow demand of the patient. Okay, we have some figures on the side. Volume. Figure 9-8. Flow time scalar on a servo ventilator during active inspiration. See text for explanation. It says here, in an inappropriate sensitivity setting and an inadequate flow setting are two causes of asynchrony between the patient and the ventilator. Next section, volume scalar, page 155. 56. Volume time scalars in this section show normal inspired and expired volumes. See figure 9-3, as well as those with an inspiratory pause. See figure 9-5. Figure 9-10A illustrates a concept that was to 156, so brief pause. Okay. Introduced in Chapter 8, what is the problem in Figure 9-10A? Asterisk, looks like the answer to that question is a system, such as a patient circuit leak or a leak through the lungs, such as a bronchopleural fistula. Okay, figure 9-10B shows another unusual volume time curve. Here, the volume drops below the baseline during exhalation. What might cause this situation? One answer is active exhalation by the patient. Observing the patient's chest and abdomen during exhalation might determine whether the patient is actively exhaling or the inspiratory time is set too long for the patient. Active exhalation sometimes is seen when air trapping has occurred. Another possibility, the flow transducer for the ventilator is not calibrated properly and needs to be recalibrated. Calibration problem was observed with an older generation ventilator. For example, the Bear 1000, Devices Corp, San Diego, California. When the flow transducer, original version, was calibrated for one type of humidifier, heat and moisture exchange, or HME, but another type was used, a heated humidifier. Current microprocessor controlled ventilators perform frequent self-calibration. Therefore, this type of technical error occurs much less frequently. Okay, and I9 says pressure and flow scalars doing volume ventilation. A, patient-triggered breath with an appropriately set sensitivity and adequate flow during inspiration. B, inadequate sensitivity and inadequate flow, or flow starvation, with a pressure time curve showing a concave or downward scoop during inspiration. Dashed lines represents normal pressure curve. Further explanation. 10. A. Scalars during the BC-CMV flow on top, volume middle, and pressure on bottom. Volume time curve during exhalation is above the baseline and resembles an igloo, a leak. B. Volume time curve drops below baseline during exhalation, indicating active exhalation or a technical error. See text for explanation. It says A, from Kakmarek, RM, Hesty, Stoller, JK, monitoring in respiratory care, St. Louis, 1993 Mosley. Looks like that was a footnote. Okay, now to the next page, 7 of Chapter 9, Ventilator Graphics. We'll read the figure in the end. Next section, volume controlled ventilation with varying gas flow waveforms. 6. Review the various flow patterns available during volume controlled ventilation and mention the benefits of the descending ramp. 11 shows a constant descending flow and a sine flow waveform with accompanying pressure scalars. Although other waveforms are available, they're not commonly used. And it looks like we have our characteristics of volume ventilation with any fixed flow pattern. For example, descending ramp, other than the constant rectangular pattern. They are as follows. The flow waveform provided, regardless of type, does not change shape during inspiration, even with changes in lung characteristics. Second bullet, the flow waveform remains the same from breath to breath. Third bullet, volume delivery remains constant as long as the breath is volume cycle. Bullet. Pressure patterns measured at the upper airway vary in C1 and the type of flow pattern selected. Yellow or C1. Volume controlled spontaneous intermittent mechanical ventilation. Let's see. Figure 912 illustrates VC-SIMV from a positive baseline. For example, VC-SIMV plus CPAP. Some clinicians refer to this as VC-SIMV with PEEP. The mandatory breaths are the same as those already discussed. The differences in this case is the occurrence of spontaneous breath. What happens to the pressure when the patient breathes spontaneous? Okay, asterisk, and the answer to that is the pressure decreases slightly on inspiration and increases slightly on expiration as well. Pressure decreases slightly on inspiration and increases slightly on expiration. Okay. Look at the flow curve. As the patient breathes in spontaneously, the flow rises. As the patient exhales, the flow drops below the baseline, just as exhaled flow does with mandatory breath. Spontaneous breaths can vary. Okay. Key points of volume controlled ventilation graphics. Next section. Let's see. Before I get into those key points, let me go ahead and read the figure. Figure 911, standard mechanical ventilator flow patterns, constant descending and sinusoidal. The flow patterns on the development of pressure is shown. Open parentheses, modified by Nilsetsuen. Target K, managing the patient ventilator system using graphic analysis. An overview and introduction to graphics corner. Respiratory care 41:1105 from year 1996. Key points of volume controlled ventilation graphics. Thus far, we have discussed VC-CMV with a constant flow. Key parts of this section included the following: observing PIP, P plateau, P tax, and PEEP on the pressure time scaler. Second bullet, on flow time scalars, locating the beginning of inspiration, the set flow, the beginning of exhalation, peak expiratory flow, end expiratory flow, and the end of exhalation. Third bullet, calculating compliance from pressure and flow curves. Fourth bullet, observing inspiratory flow of 0 during inspiratory pause. Evaluating changes in raw using the P tax, or no, that's PTA, and expiratory flow curve. Sixth bullet, increased flow with patient demand on a servo ventilator. Seventh bullet, inadequate sensitivity and inadequate flow and resulting changes in the pressure time curve. Eighth bullet, checking for the presence of auto peak using the expiratory flow curve. Measuring and observing auto peak levels on the pressure time curve. 10th bullet, checking for leaks and for active exhalation or transducer errors in volume time curves. 11th bullet, different flow patterns during volume control ventilation. VC-SIMV with CPAP. And that's the last one. It says, having completed this section, readers should take the opportunity to observe a patient receiving volume-controlled ventilation and study the available graphics. The following questions can serve as a guide. What is the flow pattern? Okay, now we are at page 158. Okay. Figure. Oh, yeah, let me read that first. Oh, it says, these concepts are sometimes better understood when they are observed at the bedside. Repeated study of graphic displays can help make the concepts discussed in this section use and remember. Okay, figure 912. It says VC-SIMV plus CPAP /P explanation from Hess, DR, McIntyre, NR, Michaud, SC, Respiratory Care, Principles in Practice, Edition 2, Sudbury, Massachusetts, 2012, Jones and Bartlett. Okay. This is pressure controlled ventilation, next section. During pressure controlled ventilation, PC-CMV, the clinician sets a pressure to be delivered to the patient's lungs. Volume vary as the patient's lung airway resistance change. The ventilator attempts to deliver the set pressure at the start of inspiration and maintain the set pressure until expiration begins, producing a nearly constant pressure waveform. Pressure controlled ventilation, next section. Ventilation with a constant pressure waveform. Pressure ventilation with a constant pressure waveform has 4 important characteristics. Pressure waveform is rectangular or constant. 2, not affected by changes in lung characteristics or patient flow demand. The rate of flow delivery varies with changes in the patient's lung characteristics, set pressure, and 4. The flow waveform rises rapidly at the beginning of during inspiration, continuously bear pattern. 913A shows scalars obtained with pressure ventilation. Ventilators operating in pressure PSV. Okay, so it's integral dash CM. Figure 9 shows scalars for a T1. Flow drops to 0 before the end of the set inspiration time. The pressure and volume scalars show an end inspiratory plateau. Pressure set by the operator and the lung pressure achieved are the same at end inspiration 9-2. Note, according to pressure should be less than 30 centimeters to 0. Greatest volume delivered to the patient for a set pressure is achieved when the pressure from the ventilator has time to equilibrate with the pressure in the lungs. Okay. 9-2. When flow drops to zero at the end of inspiration, an inspiratory pause is present. So the pressure of the ventilator in the patient's lungs. The scalars in figure 913b show a shorter, when T1 is short, short, the PL does not reach the set pressure. Therefore, no plateau pattern is seen in the pressure and volume curves. Inspiratory flow ends abruptly decreasing to zero. Notice that in this example, the delivered volume is delivered to the lung. Pressure in the lungs normally is pressure at the start of inspiration. When the ventilator starts inspiration, the AWO rises, the pressure gradient ventilator and the lung is at the highest level. Gas flow. As a result, the gas flow from the ventilator is at its greatest level. See figure 5-3. Through the conductive airways, it enters the lungs. As the lungs fill with air, ALV, approaches the set pressure. The P, ALV, are the smaller the pressure gradient. Small flow. Okay. Page 159. I'll go ahead first. It says, I'll jump to read the figure last. Now, you're 913. C dash CM bottom, volume and flow during PC dash CMD with a long T1. Alveolar pressure is equal to the peak pressure because it turns to zero before the end of inspiration. Figure is shorter. Flow does not return to short is an hold or no flow observed during inspiration. From Kaczmarek, R.M. Hesty, Monitoring Respiratory Care, St. Louis, 1993. Now to a regular text of 159. When the pressure in the lung and the ventilator when the pressures in the lung and ventilator flow drop 913A. The resulting flow is a continuously variable decelerating waveform. The volume at any point in the cycle equals the product of C1 ALV. The rate of volume fills at the beginning of inspiration. It is important to recognize that the pressure required to overcome at the beginning of inspiration when the flow is highest. Small. Therefore, it's high at the beginning of as flow decreases, assuming raw is constant. The pressure required to overcome airway resistance, or P little ta, throughout inspiration. At the end of inspiration, there is no resistance, which means that the little ta equals 0. Compare control, ventilation, and volume control. When pressure and volume are compared, the pressure and flow curves demonstrate volume control ventilation with angular flow curve, which can be with different flow waveforms. Pressure control ventilation, the flow waveform is a descent with both lung characteristics and patient flow demand. It's referred to as a continuously variable deceleration. During volume control ventilation, the pressure ascending rate or a rising exponential. During pressure control, it is assuming T1 is control ventilation, the pressure wave changes in lung characteristics. Static compliance, I believe it says C5 in its and raw. Changes in the C, little 5, change flow and volume delivery remains the same. Figure 914 changes the appearance of the flow in figure 9. Notice in figure 914 is the result of a reduction in A. The increased resistance is the result of a reduction in A diameter can occur with conditions such as COPD or again, the highest point of the start of inspiration, figure 914A. Increased resistance, the pressure does not reach as easily, which is figure 9B. Therefore, the P, which is the change in pressure, high inspiration. That's 14C and B. Rather than dropping rapidly with increased raw, the curve assumes a flatter appearance. Not drop to 0 by the T1, the lung pressures will not equilibrate. Overall volume delivery. See figure 9 dash. Next section. Figure 915A illustrates during PCCMB with no resistance. In 915B reduced by half, and the volume delivered is reduced by In figure 9.15, the resistance is increased to twice that in figure 2A. As a result, volume delivery 15C than in figure 9.15. These illustrations demonstrate the scalar changes with PC-CM, with changes and scale changes that change and resistance. And expiration. Next section. In the solid line, a typical patient pressure targeted time cycle breath. Lines shown in the flow and volume scale represent active in volume and flow delivery. Additional flow during pressure ventilation with increased effort. The function of the ventilator is to maintain a set pressure for flow. Next, time control produces a flow with diameter i.e. law. Flow through the narrow opening creates a pressure overshoot can occur at the beginning of before the pressure adjusts the set value. Okay, going to take a small break and we will go on to the next page. And Okie dokie, back from the break. Okay, I'll do the gig case study before going figure once before I go into key points. Okay. 6 first. Uh, okay, it says if the are tapered at the start, one can be adjusted over. Most care ventilators have a function for the flow during pressure. Tapering is used to pressure longer be constant, but maybe of the breath. Inspiratory flow PC-CMB, therefore can be adjusted rise time control, also called a slow 9-17. 9-1 lists the names given on different ventilators. The sloping for inspiratory rise time. The sloping or inspiratory controls the rate at which the flow valve opens. Rise time can either reduce or increase the rate at which pressure ventilator for a specific period. These changes are flow scalers, adjusting the flow delivery at the beginning may be more comfortable for the patient. They also serve as a way to ventilatory breath flow demand. In ventilator synchrony of breathing, or WOB. However, adjustment of the rise because too much tapering of flow and pressure delivery can reduce the VT or V small t patient ventilator asynchrony. Shows a series of rise time slope 2, 4, 6, 8, -10, and -12. Breath, very little sloping is used. The flow valve is delivered that is inadequate for patient demand. The pressure in your shape. During the second breath, sloping has tapered, but patient demand is still met. During the third and fourth, the flow valve opens slowly to meet patient demand. Next pressure trace, which indicates inadequate. Use thus volume. Right? Use of the inspiratory rise time, flow delivery, and thus volume delivery. Excessive initial flow has only minor effects. Initial flow, on the other hand, can have more serious consequences. Exercise 9-2. Adjustment generally is limited to pressure targeted CMV and PSV. The servo by mechanical volume targeted breaths. Or sloping feature is described in more detail in the section Pressure control MV plus CPAP. Figure 918 presents scalars from PC-SIMD plus CPAP reader with pressure targeted mandatory breath, breathing at a positive baseline pressure. That the volume for the first spontaneous breath is greater than that for the second spontaneous breath. Now, before we go on to the key points, I'm going to figure and in the case study. Figure 914, raw ventilated PC-CMD. Pressure is centimeters of H2O water. Figure A of figure, or portion A of figure 9 shows that at the beginning of the breath, the pressure gradient, change in pressure, or delta P, meters of water. The set, we set P minus PL. And then on section B of figure 9-14, L is 5 centimeters. Change in pressure is 20 centimeters. And then on part C, PL is 10 centimeters. Delta P, for the change, 15 centimeters H2O. Section D of figure 9-14 states P of PL is 15 centimeters H2O. And delta P is 10 centimeters of H2O. During inspiration is not as rapid as with normal raw. Not reach zero by the end of inspiration, lower than with normal raw. And we have a little case study question. 9-2, problem solving in PC-CMD. A patient diagnosed with ARDS is placed on MD at the following setting. Equals 10 centimeters water. 102 equals, or 8/10 set pressure, 15 centimeters H2O water. PIP equals 28 centimeters of H2O water. Small t, or V over T, equals 350 milliliters, down from 450 milliliters. Slow. Lowest possible flow delivery. Blood gas, or the ABG levels on these settings are as follows. pH equals 7.28. PaCO2 equals 49, an increase of 9 millimeters Hg. PaO2, which equals 53, down from 68 millimeters Hg. The respiratory therapist notices that PIP reaches only 23 centimeters of water. No leak is found in the system. What recommendations could you offer to improve this patient's ABGs, or arterial blood gas? That's the case study. Now we'll move on to the key points. Okay. Go into the next page. Key points of pressure control ventilation. Discuss the following topics: pressure, volume with PC-CMD ventilation, with with long and short T1. Differences in flow, waveform, with normal airways and with increased changes in volume CCMV with normal C5, and twice normal raw. Active inspiration time triggered. Next, in pressure target ventilation. The last C dash SIMV plus V. Okay. One, chapter 9, section as pressure support vent and first. Figure 915, theoretically by a microprocessor controlled ventilator operating in the pressure ventilation. The pressure setting is 10 centimeters to 0. Inspiratory time is 1.5 seconds. Milliliters per centimeter of water, H2O. And airway resistant is resistant to H2O. Can't read. Standard conditions describe B 25 milliliters per centimeter of water. H2O per liter per second. Okay, that's good. From Dupura, why ventilators and clinical applications, edition 2, St. Louis, 1992 Mosby. Pressure support ventilation. Pressure support ventilation. Patient triggers pressure targeted flow. See figure 5-7, flow pressure and volume scalars. Light negative deflection in the pressure curve, reflecting the patient's is patient trigger. The pressure remains constant, but the delivered volume effort increases the delivered volume off. In addition to the set pressure, two other parameters can be set with PSD, time or slope, as described with PCB, and the cycle value, also called the flow cycle percent. The details of the pressure time waveform for ventilation. Next section. Figure 919 shows a pressure time waveform for a pressure support. Point A is an example of an appropriate sensitivity. Evaluating the pressure time for PT. Always ensure that the sensitivity setting is appropriate for the patient so as not to make it too difficult for the patient to trigger the breath. Line 19 A illustrates an inappropriate sensitivity setting. The part of the breath breath, and pressure represented by the solid line. Oh, excuse me. Point a slope or the rise time set to that to set pressure is tapered. Set pressure is C. The arrow labeled shows an overshoot in the pressure curve. As described earlier, this is associated with turbulent airflow, which is created when the delivered pressure encounters a small ET or an obstructed airway. Also indicate that flow exceeds and over drops to its set value. See the inspiratory rise time slope artifact by limiting flow. Next. Okay, having like okay. Okay. First by reading, I will go to change that figure 916. Line represents the flow pressure and the volume scalars for PC. The dash line represents the active inspiration by the patient. The increase in volume and flow delivery. Pressure and T1 remain unchanged. Figure 9-17. Changes in the delivery system produced by adjusting the pressure slope or during pressure targeted ventilation. See text redrawn by Nielsen Stewart K. Managing patient ventilator systems using graphics. Introduction to graphics corner, respiratory care 41:1105, year 1996. As the flow percent discussed later in this chapter is reached, the pressure drops to the baseline pressure represented by figure 919, marking the reduction in pressure. D1, arrow upper right, in this curve with PS allows the pressure to increase as indicated by line. The ventilator delivers a constant pressure. This increase shows active exhalation and the breath early, which is referred to as a delayed termination, is associated with patient ventilator asynchrony. Is often seen during COPD or some other disorder that increases draw. Adjusted to shorten the T1 and lengthen should just the length in T during the PSB. See the following section on flow cycling. 9B2, figure 919 represents a rapid drop in pressure at the end of inspiration and the beginning of exhalation. Automatic tube, when automatic tube compensation is used to assist exhalation. Automatic tube compensation, or ATC, is a ventilator feature that helps compensate for the work of breathing posed by the ATC flow during inspiration. For example, the Draeger E2 actually works ET during expiration by providing a slight pressure gradient between the lungs and upper airways, facilitating exhalation. Discussed in more detail in chapter 20. Okay, next section during pressure support ventilation. Cycling mechanism of PSV chapter 3 and 5. Cycling occurs when the ventilator detects a decreasing flow, which represents the ventilator software determines the point at which flow cycling occurs. This point is a percentage of the peak during inspiration. Table 9 presents the flow cycle variables for a variety of ventilators. Unfortunately, no single flow cycle percent is ideal for all patients. Or increased raw have a slower flow rate drop off during inspiration with pressure ventilation than do patients with normal raw. See figure 914. Not drop normally. Patients with COPD are more comfortable with a higher flow cycle percent. The clinician can determine the appropriate cycling criterion by evaluating the P-T curve. If the active rise in pressure occurs at end inspiration, the may be increased to reduce the amount of expiratory work the patient. The graphics in figure 9-20 show two flow cycle percentages. What is the peak flow in question mark? Is the flow value low S? Question mark. What is the approximate flow percentage? What is the peak flow in B? Flow value where inspiratory flow ends? What is the approximate flow cycle percentage in section portion B? Let's see. It says the peak flow is about 30 liters per minute and the cycle occurs at about 5. The percent cycle is 3 or 17%. In part B, the peak flow is about 35 liters per minute, about 20 liters per minute. The percentage cycle in B is 20 over percent. In conditions marked by reduced C1, for example, pulmonary fibrosis, the lungs fill quickly during ventilation, but do not fill with as much volume. For patients the most benefit from a PS breath, longer. In such cases, the flow cycle percent, for example, 10%, to increase the duration of the breath. This allows the patient to gain as much volume as possible for the set pressure. Okay. Table 9, names and settings for inspiratory rise time and flow cycle on various ventilators. Okay. Draeger V500, Pennsylvania. We're going to state the ventilator model, the control name, and percent of peak. So the Draeger V500 time, 0 to 2 seconds. Flow cycle, expiratory time, peak 1 to 80%. Draeger E4, Draeger Medical Inc., Telford, Pennsylvania, is 0 to 2 seconds. Flow cycle controlling, there's none, but it says adults, 25% of peak, and infants and children are 6%. That might be easy.